So let's look at some questions that rely on the work we've just done on circular motion. So this one we've got a disc, it's rotating uniform angular speed of 10 revolutions per second. A point P on the disc is 30 centimeters from the center. Find the speed of P. Well, what does that mean? Well, that's going to be our radius, is going to be 30. So R's 30, and we're told that we've got a 10 revolutions per second. Now, if we want to work with the velocity is equal to omega times r, we know omega's got to be in radians. So, radians per second. So, we've got the idea we've got 10 revolutions per second, which means that in one revolution, it goes 2 pi radians. So, one revolution, 10 pi radians, and 10 revolutions would be 2 pi times 10 pi times 10, so which would give us 20 pi radians in 10 revolutions. So our angular velocity then would be 20 pi radians per second, and that's what it's got to be in. Our omega's got to be in terms of radians per second, so that's why we have to change it to 20 pi, and times the 30 means that we're going to end up with a speed of 600 pi centimeters per second. So that's how we have to calculate that. We have to do a calculation of revolutions per second to radians per second. This time we've got a particle which is 0.4 of a kilogram, and the kilograms is important there. End of a light extensible string, which is 0.6. The other end's fixed to a point on a smooth horizontal table. Now, the reason we say it's smooth means there's not going to be any friction. So that's why we use this term, smooth, there. And it's moving in a circular path on a table. So if the speed is 8 meters per second, calculate the tension in the string and the reaction with the table. Well, that's basically how it's moving. It's 0.6. Remember, if it's moving at 8 meters per second, then there's no tangential acceleration. It's all just directed back towards the center. So we're just working with the idea that velocity, we want to get our force, which is mass times acceleration, and the acceleration, which is omega squared r. So to do that, we know that it's 0.4 of a kilogram. We know it's length of 6. So there's our radius. And we know that it's moving at 8 meters per second. So our velocity there is 8 meters per second. We can get omega to be 40 on 3. Because we got 8 equals omega times 0.6. Divide by the 0.6, we get 40 on 3 radians per second for our angular velocity. So acceleration is angular velocity squared times the radius. So the 40 on 3 squared times the radius there gives us 106 and 2/3. So our force there then would be the mass times the acceleration. So the tension in the string is the force that we're talking about here. So the tension there is the force that we're talking about. And so we multiply the 0.4 times 106 and 2/3 gives us 42 and 2/3 newtons. So that's the actual tension of the string. And remember, a newton is how many kilograms per meters squared per second. So comparing the weight and the velocity acceleration. So it's the weight per acceleration there. Now, part B says if the string snaps if the tension exceeds 50 newtons, find the greatest angular velocity which the particle can travel. So we need to find omega. Basically, it means that the 0.4 times what acceleration would be greater than 50 or equal to 50. If it exceeds 50, so what's the largest value we can find? So the largest acceleration we can have is 125 there, meters per second. So what we're looking at then, the acceleration we know is the angular velocity squared times 0.6. It's got to be greater than 125, so omega squared would be 208 and 1/3, and omega then would have to be greater than 14.43 radians per second to be having a tension that would be exceeding 50 newtons. So it'd have to start moving that many radians per second there. So in the next question here, we've got a particle which moves at a constant speed around a circle of radius r. we've got V is equal to 3, radius is 6, and the force acting towards the centre is 6 newtons. Find the value of the mass then. Well, what have we got? We know velocity is equal to omega times r. So velocity then would be equal to 3r, which is equal to 6. So omega would work out as a half. So our angular velocity is a half a radian per second. And we know that the tension there would be mass times acceleration, or mass times omega squared times r. And we know the force is, the tension in the string is 6. We've got our mass, we've got our angular velocity in squared, and the 6 there. We end up getting mass, solving that for mass, gets us 4 kilograms. Question 4 here, we've got this time a mass of 0.25, and it's attached to a light inextensible string. Well, again, here's another term we're going to see, inextensible. Basically that means the string will not stretch, so it's going to stay at a constant radius of 0.5 for that circle. So the other end's fixed to a point A on a smooth horizontal table. There's that word smooth again, so we're not really taking into account any friction that's going to occur. So it's going to stay moving at a constant angular velocity. So the speed's going to be moving at 0.88 meters per second. So that's going to allow us to set up our values of mass is 0.25, radius is 0.5, and our velocity of 8. So we know that we can get our angular velocity. So we jump over here first and get our angular velocity, because the velocity is 8, r is 0.5, so our angular velocity must be 16 radians per second. And that allows us to work with the tension in the string being equal to mass times acceleration, or mass times omega squared times r. So the mass times 16 squared times 0.5 gives us 32 newtons that will be in the string. So the particle there, when it's on a flat surface, really that's exerting a force straight down there. So that if it's sitting on the table, what's the force that's exerting there? Well, that would just be mass times gravity, because it's just the mass times gravity that's moving downwards there. So the tables must be exerting the same force in opposition. So 0.25 is our mass, and we take 9.9, or you could take 10. It's going to be approximately 2.45 newtons, or 2.55 newtons if you take gravity to be 10. In question 5, again this time we've got 0.5 kilogram weight is attached to one end of a light inextensible string, length 2 meters, and it's fixed to a smooth horizontal table. The particle is set in motion in a circular path. Its string breaks when the tension is greater than 64 newtons. What's the greatest speed? So we know the force can be written as mass times acceleration times angular velocity squared times the radius. So if our force is 64, and that's got to be less than 0.5, which is our mass, and our radius is 2, so that leaves us with an equation to solve just for omega squared. So we can get our 64, because those two cancel out. So omega must be greater than 8. So that means our angular velocity must be 8. So our velocity would then be omega times 2. So it gives us 16 meters per second is the greatest speed at which it can travel. And then the last question here, we've got the mass of 2 kilograms, and it's revolving at the end of a 2 meter long string, smooth horizontal table, uniform angular speed. So the only force then means it's only acting towards the center. So if the string would break under a tension equal to a weight of 20 kilograms, find the greatest positive speed of the mass. So what does that mean? Well, the mass equals 2 lots of r, which equals 2. And taking a situation where it would be 20 kilograms there. So what we're looking at here is the mass of 2 times omega squared times 2. So mass is 2, r is 2. Just separate those there. And we get it, the force must be equal to 4 lots of omega squared. So if that's the case, then we know force must be equal to mass times gravity. And then the force then would be equal to 196 newtons. So that's what we're looking at with that question. So go through again. Make sure you're getting to use this, the force times mass times acceleration. Force is equal mass times omega squared r. Or if you want to use the velocity, some of these questions we could have used v on r, v squared on r. So we could have used it with these ones. If you want to use that, if you're used to using that as well, if you've seen that in questions and you like that, depends on what you've got and what you need to find. But if you've got that and you want to use that in questions, you'd be able to use that for some of these questions there.